Hello, all. So I put together something just for fun. I thought it was might be worth sharing, just for the feedback, just to see what people think about it. Good or bad, don't care, whatever. Um, this is about the Anthropocene, which is proposed by the ICS as a new Earth epoch. Or they have a working group trying to determine. They're supposed to come up with I think, a decision this year, 2016, and here it is, the end, and haven't really heard too much on it. There's probably a lot of political pressure around that. A lot of people are using the term, but as they're using it as a unit of the geologic timescale, but it is not a part of the geologic timescale yet. And I think the working group is trying to determine, is it going to be scientifically justified, or is it going to be useful as a formal term to the scientific community? Will the scientific community or the geologic community, by acknowledging it, will it put them in the limelight, and will that negatively impact their progress? I don't know. Not a lot of people do. All right. So just to give you an introduction, what is the Anthropocene? This is found at the ICS's website under the working group of the Anthropocene. Says that the Anthropocene is a term widely used in science, used since its coining by Paul Crutzen and Eugene Stormer in 2000 to denote the present time interval in which many geologically significant conditions and processes are profoundly altered by human activities. These include changes in erosion, sediment transport associated with a wide variety of anthropogenic processes, including colonization, agriculture, urbanization, and global warming. The chemical composition of the atmosphere, ocean, and soil, with significant anthropogenic perturbations of the cycles of elements such as carbon, nitrogen, phosphorus, and various metals. Environmental conditions generated by these perturbations, these include global warming, ocean acidification, and spreading oceanic dead zones, the biosphere both on land and in the sea as a result of habitat loss, predation, species invasions, and the physical and chemical changes noted above. So it's not a formally defined geologic unit within the geologic timescale, but a proposal to formalize the Anthropocene is being developed by the Anthropocene Working Group for consideration by the ICS, with a current target date of 2016. Now, I should note that I do not consider myself a formal scientist, but have some very basic training in math, chemistry, and physics, and I am currently pursuing an undergraduate coursework. Undergraduate coursework in the earth sciences and economics. I find both of those topics very interesting, and I'm constantly just looking at stuff, thanks to the internet and various textbooks and stuff like that. I just have my nose in those things a lot. So here's my argument for the Anthropocene, what I'm about to introduce. Before I get started, though, I'd like to give you some background, give a little credit to NASA concerning the picture you see in front of you right here. So this is an image I found on archives.org called "The Dark Side of Carbon," and this is the description. As interest in the Earth's changing climate heats up, a tiny dark particle is stepping into the limelight: black carbon. Commonly known as soot, black carbon enters the air when fossil fuels and biofuels such as coal, wood, and diesel are burned. Black carbon is found worldwide, but its presence and impact are particularly strong in Asia. Black carbon, a short-lived particle, is in perpetual motion across the globe. The Tibetan Plateau's high level of black carbon likely impact the region's temperature, clouds, and monsoon season. Image credit NASA. So I thought it was really pretty, and it may help to describe or it may help my argument along a little bit. So let's get started. So here we are. I created an Excel spreadsheet right here. When I introduced this to my physics professor, he kind of giggled. But honestly, this didn't take very long. Excel is an amazing program. Thanks to Microsoft Excel, I can, manage a lot of data, mainly my finances. So I really enjoy using this program. Let's see here. Can I get rid of this? Yeah, I can get rid of that. All right. So here we go. So here we have the entire geologic timescale in increments of 10,000 years, starting here at the Holocene epoch. That's the epoch that we are now in. As you can see, we have eons, eras, periods, epochs, and stages. Didn't really get around to putting all those in. There's far too many of them, and I think I can get my point across without them. So, just to give you an example, we are in the Phanerozoic eon of the Cenozoic era of the Quaternary period. Or sorry, I should say that the opposite. We are in the Holocene epoch of the Quaternary period of the Cenozoic era of the Phanerozoic eon. And here you'll see various columns, ribbons of color, if you will. I got the data from various resources on the internet. Forgive me if they're not completely accurate. I know that they're not, but I still think this gets my point across fairly well. So here we have modern humans. We've only been around for a couple 100,000 years. Hominids, much older, as predecessors of modern humans. They've been around for a long time. This would include Homo erectus and Neanderthals. Then prior to that, we have primates, still alive today and alive then for much longer time. And then the mammals, all mammals are considered predecessors of primates, hominids, and the modern human. Then we have amphibians, reptiles, the entire animal kingdom right here. Fishes, land plants, very important for the formation of certain fossil fuels. Coal, I believe, is one of them. Algae, now this includes various types of algae, red, green algae, and more primitive types of algae. I just looked up online. It's like, how old is algae? And, I looked at some geologic articles and stuff like that, and they said, oh, algae's this old, but, this includes this algae and that algae and whatever. So anyway, I just lumped them all into one category for simplicity's sake. Fungi, pretty primitive life form there. Put that on there. And bacteria. Now this includes the most primitive forms of life as well. And also includes the less primitive forms like gram-negative, gram-positive, and various other types of microbial life forms. But I just lumped them all into one category again for simplicity's sake. So anyway, big old ribbon. So to get started, first what I'm going to do is I'm just going to click on a single cell here and I'm just going to scroll down for a little bit. As I scroll down, you'll notice that the right-hand column doesn't move at all. It just stays relatively stationary. And I haven't done any calculations or anything to determine how long it would take to get all the way down to the bottom. But at the bottom is 4.6 billion years ago. And it's widely accepted that that's when the formation of the Earth occurred. The geologic formation, that is. And so the origins of the Earth, 4.6 billion years old. Very old. Not that it doesn't have a whole lot to do with the formation of life. What does have to do with the formation of life on Earth is stability. And so there's this hypothesis called the rare earth hypothesis, which I love explaining to my students about, it's called the rare earth hypothesis that, well, in order for life to evolve and for us to actually be here, to have developed this higher brain, there has to be quite a bit of stability. And so as I scroll down, you see this entire ribbon of life. This is all because of the stability, I believe, because our planet is very rare. Some people don't have it, don't consider that planet as rare. They think that aliens exist. And, biologic life forms may exist in the universe, but are they evolved to the level or above where we are? So, I mean, in the animal kingdom, we're a rarity, and I think that's something well worth preserving. And so anyway, the rare earth hypothesis says that you have to have the planet a certain distance from the sun. It needs to be in that Goldilocks zone, some people call it. There needs to be, it needs to be it needs to be geologically active. It needs to have a core active to create a Van Allen belt to prevent the bombardment of solar radiation that will destroy our atmosphere. I think that's what happened to Mars. It doesn't have a geologic active core or plate tectonics or anything like that to really help retain the atmosphere. It also needs to be the right size, to retain an atmosphere. The theory of relativity and Newton's second law, would dictate that, hey, gravity, 9.8 meters per second. This is what we need in order to, retain this atmosphere. Meters per second squared, sorry. And so, what was I talking about? All right, so in addition to that, we also need a large exoplanet like Jupiter to help avoid the Earth from getting bombarded by huge astronomical objects like the Levy-Shoemaker comet that hit Jupiter. So it's kind of our celestial bodyguard, I guess you could call it. And then what else do we need? We need plate tectonics, volcanic interactions with the atmosphere to pump warming gases into the atmosphere. That's required, right? So we need carbon dioxide. Carbon dioxide is actually a good thing to an extent, only to a very small extent, though. The amount of carbon dioxide we're putting in the atmosphere is much greater than all the volcanic activity around the Earth, so that needs to be considered. What else? The moon. So we need the moon and the tides, and so without the moon, we wouldn't have tides, which wouldn't put into action evolutionary triggers, which brought much of life from the oceans onto land and stuff like that. So there are a lot of things involved in the stability of our current planet, and you have to think that this is a really rare thing and it's worth preserving. So, but aside from that, what I'm trying to explain is to give the ICS or the public a reason for the Anthropocene to be a part of the geologic timescale. So here I am still scrolling. We still have, so we've gone away from primates and humans and hominids and all that. Now we're down to reptiles and amphibians. Let's just see where we're at on the geologic time period. Phanerozoic. Let's see, we're in the upper part of the Cretaceous, of the Mesozoic, of the Phanerozoic eon. So anyway, speed this up. I'm going to scroll down real quick. Meow. We're going really fast. You can see these ribbons, they just stay for a really long time. Eventually we're going to come to the end where they start to kind of go away. Really down. Okay, I'm gonna do this. Oh my gosh, look how fast we're going. This is insane. See, this is one of the problems of modern man, is that we can't put this deep time into perspective, and I thought Excel would do this. I actually got this idea. I was looking at a YouTube video where somebody had put the geologic timescale on Minecraft, and this would be awesome if somebody could come up with the geologic timescale to this degree of accuracy using Minecraft. Me, I don't do video games very often, so I just use what I have to work with, which is Excel, which I think gets the point across. So all the way down here, let's go to the bottom here. 4.6 billion years ago, right here, blah, 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 Earth's being formed, and then boom. Here, it's supposed from various resources online that life originated, or the chemical formations of life originated right here, a little over 3 billion years ago, long time ago. But aside from that, let's see what happens when I scroll up. Oh my gosh. All right, here we go. So now we have plant life formation. Now we're having photosynthesis occur. And this is where the sun's energy that actually gets here, that's absorbed by the plant, the very small percentage that's actually absorbed and not reflected back into the universe, the very small percentage is actually here, and once it gets here, it's here to stay. Okay, so it's absorbed by the plant life, and here we have the origins of algae, which is very important for the formation of petroleum, potentially the petroleum that we use today. And I know that we won't have access to all of that energy accumulation, but we do have access to a good percentage of it, I would say. So yeah, here's algae growth, and right here I put another black ribbon, and if you noticed when we were at the top, it said energy accumulation. So this is the potential energy accumulation from the life that is formed and has absorbed energy from the sun to create carbon-based matter that is just waiting to be turned into fossil fuels. And as I scroll up, you can see that this energy accumulation potentially, I'm not saying definitively, but potentially could occur over this very vast period of time. We're about halfway down the entire history of the Earth. And here we have this huge black ribbon that says that, hey, all of this energy is accumulating right here. And this explains why we have such a high standard of living today, because all of this energy that's accumulated is now being utilized right now. As I scroll up, you can see that life forms start to come into play. Let's see here. Right here, the energy accumulation, the potential energy accumulation ends. And that's because fossil fuels are considered a non-renewable resource and take about 300 million years to actually form from all that accumulation, from heat and pressure and time. But here we have quite a few animal life forms, and this is considered the Carboniferous part of the geologic timescale. We have the Mississippian and the Pennsylvanian epochs, but we're in the Carboniferous right now. So over here, and so this explains why it's called the Carboniferous, because all this carbon accumulation that we take advantage of today formed here. So as I scroll up here, it ends, and now we have all of this. And all of this potential energy of accumulation, I'm not saying it all turns into fossil fuels, but I have to imagine that a good percentage of it does, and that a good percentage of it is being utilized today to create our current standard of living and help along our technological advancement, which is great to an extent. But there's also all of these other potential impacts that are occurring, because what happens when you combust these go-to energy-dense fossil fuels? What happens when you combust them? Well, when you put any kind of hydrocarbon and you add heat, the hydrocarbon breaks off into two things, which is water, H2O, and CO2, carbon dioxide. And we don't have any use for that carbon dioxide. And in addition to that, it's also driving all of the industry, all of the agriculture, all of the meat production, and everything that we need in order to kind of get the energy that we need. And what I think this does, and this is really important, what I think this does is this creates a false sense of abundance in man. And so all of this stuff, because all of this stuff right here in this entire geologic past, because all of this is being utilized right here in this little itty-bitty cell right here. And not even this, just the very last 2%, the last 200 years of it, right here, because all of that energy accumulation is being used right there. All of that is being used right here. Is the reason is essentially just the kind of the reason why global warming is such a concern today. Yes, methane production and all this stuff, agriculture and stuff, contributes to global warming, and CO2 contributes to global warming, but all of these greenhouse gases are being added to the atmosphere. All of this energy and matter is being added to our biosphere, and it's creating changes in our environment. And not only that, the energy that we use to create compounds and stuff for use in agriculture and use in industry and stuff like that is being introduced to the biosphere because we have access to this energy. And so we're kind of in this era of gluttony where we're using it. And so just to reinforce my argument just a little bit further, I made another Excel spreadsheet of the Holocene itself, so the last 10,000 years of human civilization. So all the way down here at 7,984, I guess you would call it BC, which was 10,000 years ago approximately, humans have been around. But humans have been around, there's been less than 1 billion of them on the entire planet. Likely in a small community somewhere in Africa or something like that. But these numbers right here indicate the populations. These are not accurate to any degree, at least not until we hit the year 1800, where I actually got some data off of the internet. But these are just, rough approximations. What do you call it? Using linear math. But the actual real estimate comes at around the year 1800. And so as I go up here, we see that the population remains below 1 billion, obviously, until around the year 1800. Now, once we get up here a little ways, we actually start to see this gray thing here. And this is where we started using coal. And you can see in around the 1800, we started using coal. We see a slight population increase. Why? Because now we have the energy that we need to grow, and that's good. It's great that we learned how to grow. And then as we scroll up and we get closer to the year 1900, where the population is around 1,650,000. This is where when Spindletop was created in Texas, and this is kind of the beginning of where we start to use fossil fuels, specifically petroleum. And once we start using that, look what happens. We scroll up and bam, all of a sudden we're at 2 billion, and then all of a sudden we're at 3 billion, then all of a sudden 4 billion, then all of a sudden 5, then all of a sudden 6, then all of a sudden now we're at 7.4 billion people in the globe, and we have all of this energy to use, and we are using it. And so I think this really brings to a head the reason why we need to curb ourselves away from this go-to energy source, these fossil fuels, and why we need to put investments into other energy sources. Specifically, we need to put investments into solar energy. And that is an economic reason to justify the Anthropocene. But what is happening, and what may be a physical implication, is that we're actually taking this huge amount of material out of the ground, and it's energy dense, and that may actually be changing the physiological aspects of the Earth. And so that in itself is to me a good enough reason to make the Anthropocene a geologic epoch. And hopefully this will help people and politics acknowledge the need for alternative energy sources. and also to the need to curb population growth. So anyway, I think that's pretty much all I wanted to get across. So just to recap, here's the last 10,000 years. I'm just going to scroll down really quick. Oh my gosh, look at how much time there. 10,000 years. Scrolling, scrolling, scrolling. And there's the end. All right, and then here, oh my, here we have the geologic timescale and the origin of life. I'm not going to scroll all the way to the end, but you get the idea. So tens of thousands of those years. So it's very hard to put time into perspective, but you can see the main thing that I want to get across is that all the energy we use today comes from this mass energy accumulation from the sun, from dead plant and life matter over this vast period of time. This vast period of time. And we are all using all of this right here, and only right here. Boom. Anyway, that's my video. I thought it was worth sharing. I welcome any feedback, positive or negative. I hope this helps people explain why climate change is real, or actually I like to call it global warming, because climate change is I don't think it's a very accurate description of all the effects that are occurring. I think global warming is much more appropriate, but more so I think that another term may be in order to include all of the man-made impacts created around the globe and in our biosphere. So thanks for watching. That's it.